play actually records this. It does. Good. So our very first unit of work has got everything to do with triangles. So let's just start off with this very simple question, and that is, what can you tell me about that on the board? Just one fact at a time. Stick your hand up because it makes it easier for me to manage what's going on. Archie.
3 sides.
Okay, good observation. Might change colour too. Jeremy. So we'll put scaling with a question mark. Okay, thank you. It scares me. You must be able to tell me more than this, surely. Sophie. I think this is easier than me writing it, isn't it? Yes. X plus Y plus Z equals 180. Thank you. So 3 people know stuff. We haven't even described the shape yet. This is scary. Rosie, can you please tell us what the shape is? Yeah. Okay, what else? Actually,
I could be very wrong on this, but do the external angles do 160 degrees?
360?
Yeah.
Yep.
160.
And when we say external angles, it's actually like this. It's when you extend the line. So if I call this A, B, and C, A plus B plus C equals 360. And that's true of any polygon. Isn't that cool? Ansel? Nearly. Who can fix what Ansel just said just then? Ansel said that Y equals A. That's not quite right. There is X plus Y equals A. Did you? I thought you said Y equals A. That's true. That's called the exterior angle sum. Anything else? Okay, so it's a triangle. A triangle has properties. It has 3 sides. It has 3 angles. Those 3 angles add up to 180 degrees. To be precise, they're called interior angles. And the exterior angles add up to 360 degrees. And there's a special property, as Ansel mentioned here, that the 2 interior angles add up to the opposite exterior angle. Very wordy to say, but graphically we can see the relationship there. Why does that work? Right, so all of these are 180 because they are Rosie, say it loud, say it proud. Supplementary angles. Supplementary angles add up to 180. So because these are supplementary, that means that must be 180 minus Z. And these 2 must also be 180 minus Z because of the sum of the interior angles. So that's why those 2 add up to A. Okay. So you know what I thought we might do? And I'm going to pause the recording for this. Well, I'll explain, not for the recording's sake, but I'm going to give you an exam question. This is from, I don't know which exam, but it's a lovely exam question. It's got a couple of triangles up here, and it's a 14-marker question, which means it would be 14 minutes worth. This is not closed. This is open book. Use your calculators. You'll need them. And you can confer, use Google, do whatever you want. And I'm going to give you 10 minutes to do this 14-mark question. I'm not going to help you. Yeah, I'll get you one. I'll just pause the recording. Scientific is all. Okay. So you guys just attempted an exam question from one of the papers. And what you need to appreciate is that it was a 14-minute question because it was worth 14 marks, right? I gave you about 10 minutes to do it. No, but I gave you 10 minutes to do it because I didn't set the timer until late. So I kept on stacking the odds against you. That was deliberate because not because I wanted you to feel the pressure and crumble, but because I knew that there was no point giving you the whole 15 minutes in which to do it, kind of thing, right? So that's why. So I don't want you to feel distressed about that, and I don't want you to feel like you're all alone. No one did 10 marks worth of questions there, did they? You know what I mean? So the reason why I gave it to you is because I know that often it's useful to have something to work towards. And that trig example, I hope, by the end of probably week 2, you'll be able to do a lot more fluently and be able to do it under 14 minutes. Okay? That's why I want you to pop it away, and we'll come back to it. Don't work on it later. Just leave it. Just forget about it. I'll collect it if you like, and we'll come back to it later. So what I want to show you, and just for the recording, I'm looking at a whiteboard next to it. What I wanted to show you is that, in fact, to do what you were doing there required an understanding and fluency in the sine rule and the cosine rule, to understand the ambiguous case of the sine rule to get different angles. Lots of little bits and pieces. It's a beautiful question. It really is. But, of course, you need to know that sort of stuff. Okay, now looking at the whiteboard, you can see I've got a set of levels here. The roll gold sort of stuff where we need to work towards is trigonometric functions. That's going to happen in week 3. What we're doing in the first 2 weeks is triangle trigonometry. Okay, if you could just let me go through this. So where the question you attempted just then is non-right angled trigonometry, where you are attempting to use rules or trigonometric calculations in order to solve problems with non-right angled triangles. Neither of those two triangles are right angled triangles. Okay, so in order to develop an understanding of non-right angled triangle, we need to understand right angle trig. Can you see what I mean here? That if we get an understanding of this, then this builds on this. Okay, to understand non-right angled triangles, we need to make sure we're solid with right angled triangle work. And in order to understand right angled triangle work, we need to know a little bit about triangular properties, which is why I started with what you can see on the screen right now. What is it about this? Okay, so I wanted to set the scene for you so that I'm really hoping in a couple of weeks' time, when we return to this trig example that I just gave you, you'll actually be able to look at it again and say, actually, I reckon I can do it now. You might not yet be fluent, but you'll be closer to it than you are right now. Okay, so that's what you just did, a little test. And we're now going to have a look at this. This is a right angled triangle. Tell me some particular properties about a right angled triangle. Sophie, for one, please. Yep. How many 90-degree angles can we have in a right angled triangle? A maximum of? Yeah, because if it was 2, we wouldn't have an angle to make the third line, to make the third side, right? Zoe. Beautiful. Technically or typically, we use that hypotenuse we call C. And so we just say C squared equals A squared plus B squared, but more beautifully as Zoe said it. The hypotenuse is the special word that Zoe used, so we'll put it there. What is the hypotenuse? There are 2 ways we can describe the hypotenuse. Give me one of them, someone, please. Jeremy? That's not one of them. Any 3 of those sides there could be talked as the shortest distance between 2 vertices in a triangle. So what's specifically about the hypotenuse makes it that? Ambrosia? Yep, it's always opposite the right angle. And Ansel? Always the longest. Good. Always, always, always. You cannot have a right angle triangle where the hypotenuse is shorter than either of the other 2 sides. You can get close, but you can't do that. So all of those things are true. Now, let me label one of the angles here. It's theta. What can you tell me about the missing angle? Tara? Close. See? Sorry, Tara? Absolutely. So what will that angle be then? Nah, because it depends on theta, right? So you were right that you said theta plus 90 plus whatever that one is would be equal to 180 degrees. So what does that mean about that one? What does the question mark end up being then? Love to see your hands up because that muttering actually confuses what's going on. Ansel? Yeah, it has to be 90 minus theta, right? For two reasons. Number one, if I subtract 90 from both sides, I get theta plus question mark equals 180. And then if I subtract theta from both sides, I get 90 minus theta. But for a smarter reason, I suppose, is that not smarter, but just as obvious reason would be if this is 90, these two have to be 90. So if that's theta, that has to be 90 minus theta, right? So there's the special relationships of the right-angled triangles right there. So there we go. There's the start. I'll zoom them all out so you can see all four slides at once now. So you can see the success criteria for today are as follows. Number one, I can recall basic facts about triangles. We did all right, didn't we? We wrote down heaps of stuff, even the exterior angle sum thing, which I wasn't even expecting. Identify trig ratios. I haven't done that yet. What does that mean? That second dot point. The third dot point, find missing sides and angles in right-angled triangles. We haven't done that yet. So we've really just nailed that first one, though. We know some basic facts about triangles, and we know some specific facts about right-angled triangles. Okay, so how do trig ratios work? So I heard Rosie say Sokotoa. I think you've all heard that before. Yeah. So I don't think I'll explore this. I think I'll just quickly explain so I can move on. The idea is that if I draw I can draw lots of different kinds of right-angled triangles, like so. Excuse the fact they're not actual lines, but you get the idea. I'm going to erase this in a second. So this is just for looking at. All of these are lots of different right-angled triangles. They look different, and the reason why they look different is because the angles inside are different. Okay, so I'm going to erase all that, and I just want to point out as clearly as I can without taking too much time that if I draw one that looks like this, oops, and one that looks like this, and then one that looks like this, they are all the same triangle except different sizes. They look the same except being bigger or smaller. Yeah, thank you. So we call these similar triangles. Do you remember that from grade 9, I think? Similar triangles. And there are things that make triangles similar. One is side, 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 I think. No, that's congruent, actually. But one of the critical ones is angle, angle, angle. Okay, so angle, angle, angle means that if the three interior angles of two triangles are the same, then those two triangles are similar. Yes. So if we call this 1, this might be 2, and this might be, let's just call it 3 for the sake of it, 1 to 2 to 3. In other words, the third triangle is 3 times as big as the first triangle. The second triangle is 2 times as big as the first triangle. So they're in direct proportion to each other. And I think this is what you did actually ask, Archie. It does mean that every single side would be in proportion to each other. So let's call this x. That would be 2x, and that would be 3x. Right? If I call this y, this would be 2y, and this would be 3y. Yeah? If I call this z, this would be 2z, and this would be 3z. Now, I've just chosen those scale factors arbitrarily. I could create a triangle that was 0.5, half as big, or 1.6 times as big. Pi, the scale factor could be pi, in which case it would be pi x, pi y, and pi z. So it's just a scale factor. It's just a number you multiply each side by, it will make a bigger or smaller triangle. Is that okay? Okay. You okay with that? Okay. So let's do something fancy schmancy and say, here is an angle theta. Now, because these are similar triangles, this must be theta and this must be theta as well. Correcto? Now, angle is a measurement from a point looking in one direction and turning to face another direction. That's what angle is. So you stick on one point and then it's the measurement of the turn between two viewpoints effectively. Okay, so from theta, we can talk about this side here being opposite. Then we've got two sides that are next to the angle. They're called adjacent sides, just by in the regular English definition of adjacent, means next to. But Z already has a word because we looked at it last slide, and we call that the hypotenuse. So therefore, this is just left as the adjacent. Okay, it's left as the adjacent. So we can label the three sides of the triangle according to the angle we are sitting on, or the vertex we're sitting on, if you like. Okay, so from this vertex here, if I call it, say, for example, vertex A, then from the vantage point of vertex A, we can label the sides like so. Now, why is that important? Well, without looking at SOHCAHTOA, let's pick two sides at random. I don't know. How about the side that's opposite, which is X, and the side that's the hypotenuse, which is Z. Those two sides in the first triangle are X and Z. Here, they are 2X and 2Z, and here they are 3X and 3Z. Now, look what happens when we compare the ratio of the two sides. Now, when you hear the word ratio in mathematics, it either means 1 to 2 like that, or it means writing it as a fraction. So let's have a look at what the opposite over the hypotenuse looks like as a ratio. It would be X over Z. Happy with that? Well, what happens when I do it in the bigger triangle? It would be 2X over 2Z. And this one here is 3X over 3Z. Okay? I'm just comparing exactly the same pair of sides for each triangle. Note that theta hasn't changed position. So the value of theta is the same in all three triangles because that's what makes a similar triangle similar. And its position, its vertex hasn't changed position. So we're still looking at the side opposite and the hypotenuse. Now you have a look at this one here. I'm going to zoom up so you can see it. This ratio in the middle triangle is 2X over 2Z. Well, if I simplify that, the 2's cancel out, I get X over Z. If I do that for the third one, the 3's will cancel out this time, and I get X over Z. And you could imagine it doesn't matter what the ratio, the scale ratio is, the scale will cancel down, and I'll always be left with X over Z. Now, the critical property of this means that in a right-angled triangle, as long as the angle is constant, then the opposite over the hypotenuse, the value for the opposite over the hypotenuse will always be the same value. In other words, here, if I divide the opposite by the hypotenuse, I get a number. Here, if I divide the opposite by the hypotenuse, I get exactly the same number. And here, if I divide the opposite by the hypotenuse, I get exactly the same number every single time. This is the basis of trigonometric ratios. Because that value is exactly the same for that particular angle, then I've got a number that never changes for that particular angle. So what I do is I call that a function. And if I put in that particular angle value, I will always get out exactly the same number. Okay. So for example, if this was 45 degrees, this would be 1, and this would be the square root of 2. And the ratio would be 1 over root 2. Okay. Always. This one here would be 2. this would be 2 root 2, and we would work out the ratio again, and so on. So the ratios remain constant. Absolutely critical, because a lot of people don't really get what sine, cos, and tan are. They are just a comparison between two sides, and the value is received. Now, the good news is that we can therefore take any old triangle, right-angled triangle, sorry, measure a certain angle, and then divide one side by the other side and get a value. And then we can do that for 1 degree, and then 2 degrees, and then 3 degrees, and then 4 degrees, and do that all the way up to 89 degrees. And then someone else might go and do it for half degrees and work that out, and then have this giant, massive book. I used to have one, but I don't have one anymore. But you could imagine a big book with these things called trig ratios. And so if you had a triangle with a missing side, or but you did know the angle, like this. So for the video recording, I'm just drawing a little triangle off to the side here, just so that they can see what I'm talking about. And you didn't know the hypotenuse, for example. Well, you know that 12 divided by the hypotenuse is always going to be a certain special value. So you would go to your trig table book, and you would look up 37 degrees, and you'd go across and you'd say, oh, that happens to be some sort of value, which you would put in here. And then you could work out the unknown, because it's an equation with just one unknown. Now, of course, we don't want to have to carry lots of books around, which is why all of those trig values have been condensed and put into a little electronic device we like to call a calculator. So instead of looking it up in a book, you can simply go sine 37. And sine 37 would give you what you're looking for.
So when we do like big, long, really specific numbers, sine, tan, are we actually getting a bit of an approximation now?
Yep. Yeah. Not always. Sometimes they're exact.
But if you're doing like a really obscure number.
Now, because you're year 12s, and because I'm assuming you've done year 10 maths, I'm going to leave it as that as a reminder. So the 3 possible ratios, if you think about all the possible combinations, you've got opposite over hypotenuse, you've got adjacent over hypotenuse, and you've got opposite over adjacent. The only other ratios you could have is simply to flip it around, like hypotenuse over opposite, or hypotenuse over adjacent, or adjacent over opposite. They also are trig functions, but they're not really necessary to study at this level, and nor are they anything special. They're just effectively just the flip of those trig ones. So just to remind you, SOHCAHTOA is your memory aid to memory, and it means sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So we normally call them sine, cos, and tan, with the 3-letter abbreviation SIN, COS, and TAN. Okay, so we use those to solve problems like this one. Now, I'll leave this zoomed out now so you can see the notes. And I'll just do a quick solution and get you stuck into doing some work. So let me just go through it maybe, yeah? So let's just say we're trying to find the value of x in that triangle there. So, oh, that's right. I meant to say that. You've got it on the top there. This is what I recommend you do permanently until the end of the year. Set your graphics display calculator into radians. Ask me how. And leave it in radians. Set your scientific calculator degrees and leave it in degrees, so that when you pick up your calculator in an exam, you just pick up the one which is relevant, and you don't have to you don't do how many hours work, yeah, using the wrong angle. We'll talk about radians specifically later. We're just starting off with degrees right now. PS, bring both to class from now on. Did everyone hear that? Jeremy, did you hear that? Great. Okay, so what we do is we set up the problem. This is the way I do it anyway. I set up the problem by identifying what I need to know and what trig ratio will get me there. So here's what I need to know. I need to know the hypotenuse. So out of the 3 trig ratios, sine and cos deal with hypotenuse, right? Soccer, because toa is opposite and adjacent. I remind myself that if this is where I'm standing with the angle, then opposite would be this one and hypotenuse is here. So the one that deals with opposite is SOHCAHTOA, so it's SOH. So I would start, personally, I would start with the sine of 30 degrees is equal to opposite over hypotenuse. Now, personally, first of all, you will often find that brackets aren't used in many instances. I tend to use the brackets to remind myself that I'm dealing with a function, okay? I've seen lots of people forget that they're dealing with functions and just write sine 30, which is a legitimate way of writing it, but they forget, and then they do things like divide by sine. You can't divide by sine, just like you can't divide by f in f of x, right? It's a unit. So sine of 30 is a unit, and it's equal to 10 over x in this instance. Now, we just need to do some basic algebra manipulation to get x by itself on one side and a whole bunch of numbers on the other. Personally, I keep sine 30 like that. I don't calculate it because as soon as I turn it into a number, sometimes that will make it an approximation. So if I leave it to the end, it's a little bit better. Now you can do this in one step. I'm going to do it in two, just so you've got it there. Multiply both sides by x, and I get x sine of 30 is equal to 10. And then if I divide both sides by sine 30, I get x equals 10 over sine of 30 degrees, which should give me 20, I think, if someone wants to work out on their calculator. Yeah, sine 30 is one of those really common ones, and I know sine of 30 is a half. So 10 divided by a half is 20. Yep. Yes. Yep. Yes. And your radian equivalents. 1060. Root 3, I think. It's either root 3 or 1 on root 3.
We should have memorized some of the more common ones.
Yeah, anyway, can we just move on here? So that last step there, which I did in my head, is a calculator operation. Now, because you've done trig before, I'm not going to make you do it right now. Just assume that you're okay with punching buttons on your calculator. So that's how you do that problem. Here's example 2. So we've got a 45-degree angle here. We've got two sides that we know, and we need to work out this side here, the hypotenuse again, which I'll call x. I might just zoom up for this because there's nothing else on the screen. So we just start off the same way. We've got two sides here. So we can use either of those two sides. This is not what I meant to do. Darn it. No, you can't. Well, you can. You can use Pythagoras. This is actually not what I meant to do. So you know the answer, right? But what I meant to do was actually put the angle in. That's why it's a second example. Sorry, otherwise it would have been just the same as before. Imagine you've got theta there and 10 and 10. I wonder what the angle is. It's pi on 4, of course, but let's do it in degrees. So we start off the same way. We go, I've got theta. This is what I need to work out. Okay? From the angle, I've got opposite and I've got adjacent. I don't have the hypotenuse. So that means that knocks out sine and it knocks out cosine. So I start with tan because tan is opposite over adjacent. And I have tan theta is equal to opposite over adjacent, 10 over 10, which of course equals 1. Yeah. Now, because I know my trig ratios really well, I know that theta is therefore equal to 45 degrees. But what you do on your calculator is basically this. There's an operation on your calculator, which is tan to the minus 1. Now, the good news is, I love this fact, because you're IB math students, you might recognize that to the minus 1 is an inverse function. That's where it comes from, right? That's why we use tan to the minus 1. So when we say tan to the minus 1 of tan theta, we know that when we apply the inverse to a function, we're just left with the input. That's where theta comes from. And on the right-hand side, we will have tan inverse 1 of 1. In other words, we're saying tan is a function, If the output was 1, what was the input? And the answer is 45 degrees. Okay, so there's your use of inverse functions again to figure out the problem. So you used it, so literally on your calculator, you'll go second function tan, type in 1, press equals, and it will say 45 degrees. Hey, although that was perfectly legit what I did there and deliberately did it that way in order to show you how to work out the angle, what would have been the best way to do it? Nope. Sorry?
The sides are equal, so you know that the angle is
Thanks, Rosie. Yeah, exactly. Yep, I know the diagram's not great, but it's labeled here, isn't it? So it's an isosceles triangle. The sides are equal. That's what Rosie said. If we know that if the sides are equal, the angles are equal. If 90 is taken up here, each of these must be half of 90, right? 45 degrees. That's a lot less intellectually challenging, but requires a bit of forethought than having to do this where you might make a calculation error. Okay, I'm actually going to leave it there. We've got 10 minutes left in the lesson. I want you to start at exercise 11A on page 367. If you look at those and say, I need a bit more of a challenge, just hit up question 7 straight away. When we get to class next lesson, can you please continue on with exercise 11A? And I will start the lesson formally about 10 minutes in after that.